much, Mary Jane.
Okay, thank you very much, Werner, and I want to thank the CHPC for giving SWAS an opportunity to share with all you stakeholders work that we are doing in collaboration with the CHPC. I'm going to share my slides. So Werner, I'll ask that you confirm that you can see these okay. Do you see them fine in presentation mode? Okay.
Yes.
All right.
Good,
okay, thanks Werner for confirming. So colleagues, as Werner has indicated, there'll be two of us that are speaking, and both Michael and I are PIs on the CHPC. There is also another PI at SWAS who is Stephanie Landman, but I'll speak to some of her work as well in this presentation. So as the South African Weather Service, we are an entity of the South African government, and our mother department is the Department of Forestry, Fisheries and the Environment. And our mandate is to provide weather and climate information. Our mandate has since been extended to also include air quality. So we do make, ongoing observations across the whole of South Africa, as well as in the surrounding oceans. By law, we are the only organization within South Africa that may issue severe weather-related warnings over South Africa. And this is to ensure that there's a single authoritative voice in this regard. We have got a number of designations from the WMO. We're a regional specialized meteorological center. We are also a regional training center, and this means we have got some responsibilities, when looking at the SADC region, and I'll show some of the work that we are doing as an RSMC. Additionally, we are also a global producing center for long-range forecasts. I will not touch on this, but what this means is that we also produce seasonal forecasts globally. We run a global seasonal forecast model on our in-house HPC system. At SWAS, we work with what we call a seamless system. And by seamless, we mean that we can work from the very short range time scales. In terms of what's happening now, we call that nowcasting. And we work all the way across up to multi-decades. And that is, normally when we talk climate change projections, we will be looking at, say, 30-year averages or something like that. So at SWAS, we do have systems that go along from minutes, as I mentioned, from nowcasting. And in this talk, I will be focusing on modeling. So for us to say anything in terms of forecasting beyond 2 hours, we rely on numerical models. For the nowcasting part, we rely on the radar network as well as satellite observations that I will not touch much on. But for those who are interested in that type of information, we are available to provide information on these. So in terms of how atmospheric models work, or really this speaks to why we need HPC systems, we solve some equations, and then in terms of the main ones that we are focusing on, we look at momentum conservation, mass conservation, so that is the continuity equation, as well as energy conservation. And our models need initial conditions, and these come from our observations, and the models also need boundary conditions. The simple way to think about the way the models work is that everywhere, I'm showing you a globe there that shows some lines of longitude and lines of latitude. And the way to think about these models is that where these lines meet, that is where the calculations are made. So when you want to think about resolution, when it comes to these models, you think about the distance between two consecutive lines. So if the line if the distance between two parallel lines is large, that means the resolution that you have is relatively low. When we were starting with modeling, the resolution was generally really low. And as time progressed and computational resources improved, the resolution that the models are running with continued to improve with time. We have got what we call limited area modeling. And when we use these limited area models, we are able to reduce the distance between these parallel lines that I've spoken to, which talk to high resolution. With limited area modeling, what we do is we focus only on the area that we are interested in, and we get input from a global model that will then provide us with time-dependent lateral boundary conditions. And most of the work that I'll be showing you here actually uses this technique called limited area modeling. So when we look at what is happening across the whole of the continent of Africa, and looking at numerical weather prediction, we don't actually have any centers that are running these models globally. Even, with us at SWAS, we only run limited area models when it comes to numerical weather prediction. But as I mentioned, where I was just starting to introduce SWAS for seasonal forecasting, we do run a model globally. So most of the results I'll be showing in this talk will be focusing on a project that we ran in collaboration with a number of countries within SADC. So we were running this project with Botswana, with Mozambique, Namibia, Tanzania, as well as Zambia. And we also collaborated with NASA in the US, as well as with the UK Met Office and University of Reading. And for this project, we had HPC specialists. So in our case, for South Africa, it was us at SWAS, as well as the CHPC who were participating in the project. And for all the countries that I have listed, we had the HPC specialists who host HPC centers in those countries, as well as the med services in those countries. With this Climate Research for Development project, the funding came from the UK, and the research grant manager was the African Academy of Sciences. And there is also funding from the Department of Science and Innovation to assist with the implementation of the SADC Cyber Infrastructure Framework. And when we ran some of the workshops, or when we were writing some of the papers, we actually got support from this funding from DSI to make some of the activities possible. So I'll touch very briefly on the research conducted for all the different countries. But in particular, I've already mentioned the research focuses on numerical weather prediction. When we look at the models, I already mentioned the issue of resolution. There are still processes within these models that we are not able to capture explicitly. And what we then do as a community is we've got what we call parameterizations. What these do is they represent statistically the influence of the subgrid processes that the models are not able to capture explicitly on the large scale processes that the models are capturing. What we decided to do was then have people looking at different research questions from the different countries, and I'll touch on all of these. So for our project to be successful, we had to run some workshops. We ran the first one at SWAS, which happened on 26 to 28 August of 2019. And for these workshops, we had the weather scientists, as I mentioned, from Med Services from the 6 countries participating in the project, meeting with HPC scientists and implementing WRF in each of the HPC systems from these countries. And for that particular workshop, we also had Anne Friedland from NASA participating. Then she invited some of her colleagues to present on the radar software, as well as WRF sensitivity work that they have done, as well as satellite observations that are available. Then at the CHPC national meeting in December, we had two sessions that ran, one on 1 December 2019, where again the different countries were represented together with scientists from Brazil and Russia, where there were some presentations made on numerical work that is taking place in the different countries. Then on 3 December, we had an applications workshop. Again, all the countries, the 6 countries that I've mentioned were represented in these workshops. And the funding, as I mentioned, came from CR4D as well as from the Department of Science and Innovation here in South Africa. So I'll start by just showing some, now it's just results. I'll be jumping from one study to the next. And I have to mention for all the studies, there are papers that are out, so that if you want to get more information on the studies, you can visit these. At SWAS, we conducted a study where we were comparing 3 different models, and we decided on these models because we conducted a survey that indicated that these are the models that are being used within SADC region. We've got COSMO model, whose development is led in Germany. We've got WRF, whose development is led in the US, and the unified model, which is the main operational model that SWAS is using. And we identified a number 11 high impact weather events and made simulations on the CHPC. And we compared the simulations with our ground observations at SWAS, as well as some of the satellite-based observations. In that figure there, I'm showing you simulations. There's COSMO, there is the simulation, WRF simulation, as well as GPM, which represents the observations. And you can see that all in all, we can say all the models do capture these high impact events. We found a similar result actually when looking at all these, at all the 11 high impact weather events. But when looking at the detail, for example, you can see there by Lesotho, when you look at GPM, which I said represents our observations, you can see there's some rainfall there, which there was a coastal low there that resulted in some rainfall that WRF captured, but COSMO and the were not able to capture that. So it's just really when looking into the details. But all in all, if there is a really high impact weather event that is coming, all the models will be able to capture it. The results from this study, where we picked only 3 of the events, will be published very soon in the South African Journal of Science. I think the publication, the paper should be published in the next few days. Then for Botswana, we used WRF and compared 4 different microphysics schemes. We ran WRF first with data from the global forecast system. So this is a model that is used in the US. We had a bigger domain that you can see there, and then the red one is a smaller domain where we're running with a grid length of 3 kilometers. And as I mentioned, the idea here was to compare 4 different microphysics schemes. And the simulation was made for the tropical cyclone Dineo. So simulations were made for the year 2017, and we made simulations for 17 February, 18 February, as well as 19 February. The plot that I'm showing you there, those are not simulations. These you can think of as observations. So the first row is 17 February, second row is 18 February, and the third row is for the 19th of February. Then in terms of the columns, the first column represents station data. The second column are the ERA 5 reanalysis. So we think of these as observations. Then the third row is GPM or IMEX. So this is a satellite rainfall product from NASA. Then the last row is TAMSAT, which is a rainfall product from University of Reading. So as you can see, all of those, so basically what is represented in the first row is supposed to be all observations. And you can see when looking at these different rows, there are differences, which is a challenge that we keep finding on our continent, that what we are supposed to be using as observations actually look very different from one another. Of course, that first column there represent what we saw on the ground, but these are observations. They are you can think of them as point observations. So our results from this study indicated that there's not much of a difference when you look at simulations with different microphysics schemes. In fact, the simulations kind of looked more similar to one another than they did to the observations. A good example that you can see there is on the last line there on the plot, which reads inner domain hourly rainfall area average. So there we are showing the area average rainfall in the smaller domain where we used a 3 kilometer grid length. And you can see that those different colors from the model simulations. The red color is the ERA 5 reanalysis, and it kind of goes along with the simulations. But when you look at the GPM from NASA, is very different. So the timing of rainfall according to GPM is actually very different from what the simulations seem to suggest. Then for Zambia, we compared 3 different case studies. And with Zambia, we're not looking at different microphysics schemes, but rather at planetary boundary layer schemes. So we selected both non-local schemes as well as those that are TKE based. So for all the studies, we selected events that were kind of associated with some raging high pressure systems. So with raging high pressure systems, it's actually the Atlantic high pressure system, which extends eastwards and transports moisture from the Indian Ocean over land. And this generally results in some rainfall. So you can see, so there is an inner domain there where we ran the model in the southern parts of Zambia with a grid length of 3 kilometers. And in the bigger domain, we ran with a grid length of 9 kilometers. And when we got to 3 kilometers, we switched off the convection scheme. Again, here I'm showing you different observations. IMEC is that GPM that I showed for Botswana as well, which is a NASA product, and TAMSAT is a University of Reading product. And if you look at the first row, it's showing you the observed rainfall on 17 December, and the second row is observed rainfall on 21 December. And you can see again that there are differences in what we call observations. Again, a challenge when you are running a model, the question is, what should you be targeting? And as a continent, we know that we've got sparse observations. Then looking at the simulations, as I mentioned, for 9 kilometers, we left the convection scheme on, and for 3 kilometers, we left the we switched it off. And you can see that the bigger differences. So this is looking at the 4 plots. So basically the 2 columns at the end there, those are different simulations made with the planetary boundary layer schemes that we are testing. And you can see that in general, they look kind of the same. Then the biggest difference that we realized is that when you switch off the convection scheme, you actually start capturing larger rainfall intensities. But if you keep it on, then there is no benefit of higher resolution. Then we also looked at the planetary boundary layer scheme. So it's one of the variables that are of interest when looking at planetary boundary layer schemes. In large eddy studies, they find that when they reduce the resolution, the boundary layer height actually keeps increasing and increasing. In our case, we didn't have observation of the planetary boundary layer, but we just wanted to compare what the different convection schemes give us. So in the end, we could say we like a bit what YSU was giving us, also in comparison to what the temperature simulations were about. So in the end, we kind of said YSU, which is Yonsei University Planetary Boundary Layer Scheme. It's a non-local scheme which also takes into account the effects of shallow layer clouds, was recommended. So we also conducted a study for Namibia. So with Namibia, we wanted to see the effect of multi-nesting. And by this, I mean, I mentioned the process of doing limited area modeling to say, is it necessary to first go to 9 kilometers before going to 3 kilometers? And we also tested the effect of just switching off the convection scheme, for different resolutions. And so what I'm showing now in this plot, you can see some of the simulations show high rainfall intensity and then some do not. So the first row, you can just think of those as observations. The one is the ERA 5, and then we've got IMEC as well as TAMSAT. Then the 5 are all simulations, and everywhere where we say no Q, that is where the convection scheme was switched off. And you can see when you look at the rainfall intensity, you see much brighter colors, or colors that are going more towards red when we switch off the convection scheme. So we didn't really see much of a difference when we went with multi-nesting, versus single nesting. But obviously, I mean, the model developers continue to recommend that when you run a limited area model, in terms of the ratio that you used, it has to be 1 to 3 to 5. So which means you can be going maybe from 1 to 8 when it comes to the resolution differences between the model that is forcing the inner child model. So we did a study also looking at the Idai tropical cyclone. So this one was done in collaboration with Mozambique scientists, and we made 72-hour simulations. For this one, it was just one, in terms of nesting, it was just going from GFS to WRF at 6 kilometers. And we compared 5 different convection schemes and we also made a simulation where the convection scheme was not switched on. So this particular model, the particular tropical cyclone, the models actually did very well in capturing it. So this is also in terms of, the operations. And when we look at 24-hour rainfall, so I'm showing you the example from all the different simulations, and you can see they generally agree with each other. But then we found that when we compared the types of convection scheme against each other, we found that those that are scale aware actually produce less rainfall compared to the convection schemes that are not scale aware. So the two that are scale aware, and by scale aware, I mean, they know that as you increase the resolution, you have to, the convection schemes or the parameterization is supposed to start contributing less to what is being simulated. So that GREL-F there, as well as MSKF, when you look at the amount of rainfall they simulated, it's slightly lower looking at that first column. So that is the rainfall from the convection scheme. While BMJ, NUSAS, as well as TIDGE, they are generally thought of as not being scale aware. They were not able to capture this difference. So all in all, we can't say, because when you look at the observations, like I said, if you combine the full rainfall, you'll find they are mostly the same. But all in all, we realized that when you use scale-aware schemes, they know that they need to do less as resolution increases. And we expect that when looking at processes that are less strongly forced compared to a tropical cyclone, we will see larger differences. Then for South Africa, also just looking at our operations, we also conducted a study where we wanted to see how we did in terms of just our operational forecasts with the Idai tropical cyclone, as well as the floods that occurred on 23 April over KZN in 2021. In 2020. So Here, first, I'm showing you what our operational structure looks like, as well as the HPC system we have got at source. We run the unified model, which is the main operational model used at source over the whole of SADC, and you can see it there. And over South Africa, we are running with a grid length of 1.5 kilometers. And as Verna mentioned in the introductions, we have got a failover system with the CHPC. So if we experience technical difficulty with our CRAE there, we run our forecast on the CHPC. We update our forecasts 4 times a day. So with the ditropical cyclone, we found that actually the forecasters were able to pick this up actually well in advance, even 4 days before the Idai made landfall. The forecasters were already giving indications. So this is for our regional specialized meteorological center. So this information where you see this green line showing the amount of rainfall expected, with different lead times, was available to different forecasters in different SADC countries. And we also found that the Southern African Flash Flood Guidance, it's a system that provides information on basins that are likely to flood. So we also made some comparison looking at the KZN flood, as I mentioned, and we compared the with different resolutions as well as ECMWF data. All in all, we found that ECMWF actually outperformed the for this particular event. So more information on this paper, on this work is published in a paper already published with the South African Journal of Science. I see I'm running out of time because Michael needs to speak, so I'm going to jump these and get to my concluding slide here, which speaks to the model development that we are doing at SOurce. So we are working with University of Witwatersrand, University of Pretoria, Northwest University towards improving the CCAM model. So we've chosen CCAM. It's a conformal cubic atmospheric model, which was developed in Australia as a model that we are going to be using to develop model development capacity in South Africa. So I think with that, it's Michael, you can take over.
Thanks very much, Mary Jane, and thanks to CHPC for the opportunity. I think you can go to the next slide, Mary Jane. So I thought I would just give a brief introduction of the SWAS Marine Unit. Our collaboration with the CHPC is relatively new. So I thought I'd just give an overall impression of what we are about. So we were only established in 2018, and we have a focus on developing operational oceanographic tools, specifically for the more coastal areas, for both public good and commercial clients as well. And we have a sort of policy of publication of all of our tools and research. So we try and publish on all of the tools and applied research that we do. You can go to the next slide, Mary Jane. So we're relatively new, as I mentioned, and you may wonder why the Weather Service has recently invested in our maritime forecasting capability. A good case study of this was Cape Storm, which happened in June 2017. Some of you may remember the large Knysna fires that resulted from this weather system, and those of you living in Cape Town may have also seen some of the oceanographic effects, and some of them are pictured here. What resulted from this, if you go to the next slide, Mary Jane, is that we noticed that there were some gaps in the information we could give to our forecasting divisions and also to the public on maritime effects of this weather system. So some of the key questions we weren't able to answer was what were the global forecast systems that are freely available, were they actually reliable for this event and other events? And more importantly, if it is reliable, how would those waves manifest in the nearshore? An example of this is shown in the bottom right, where you see the low resolution of the global models. And you can see where everywhere there's purple, there's no wave information given. And that's almost for the entire coastline, or at least the near shore of the coastline. So how the wave forecasts manifests in somewhere like Table Bay or somewhere like False Bay was not explicitly known. The other factor that we didn't know at the time was water levels. So how is storm surge going to affect the coastline, and how is the interplay between water levels and waves and other phenomena going to impact on the coastline? You can go to the next slide, Mary Jane. So this brought about the development of our operational forecasting capability, the SWAS model. You can go to the next slide. And this forecast system is a coupled wave and hydrodynamic model. It's written in using the Dolph 3D software. And we give a 72-hour forecast of both waves and water levels for storm surge. One of the keys to the success of this forecast system is our input of high resolution atmospheric data, which is given by the unified model, which runs at a 4.4 kilometer, which Mary Jane explained. And we run it twice per day. This produces 6 kilometer horizontal resolution waves and water levels for our entire coastline, which is roughly about 4 times as high as any of the freely available products that you'll see on open source kind of websites. And on top of that, then we also give 2 kilometer horizontal resolution waves around more economically sensitive areas around our coastline, which is essentially all the major ports around our coastline as well. I think you go to the next slide, Mary Jane. So how does this look? Well, luckily 3 years later, we had another very similar weather system to Cape Storm. That was in July of last year. And it was very interesting to compare these two systems, because now we had the high resolution coastal forecasting capabilities, and now we're able to give our forecasters and other stakeholders really good information, and both in nearshore waves. So you'll see our plot on the bottom left now gives those wave heights in the Table Bay area, as well as how the waves refract around False Bay. So if you're standing, say, near Strand on the eastern side of False Bay, you're going to get much more impactful waves than you would, say, if you're at the Simonstown Naval Base. So we can really give that really good information in terms of wave forecasts, as well as storm surge. So you can see on the right panels our storm surge forecast for that day. And although no inundation warnings were given, the storm surge has a big impact on how far your waves are going to reach into the coastline. So we're able to really give good information. And you can go to the next slide, Mary Jane, and you'll see that our forecasters are now through the impact-based forecasting system, giving this kind of detailed information. And on the right, some pictures of some of the effects that happened more specifically in the Cape Town area. You see on the top right, some infrastructure damage, and on the bottom right, a ship nearly ran aground, in fact, in those conditions. So really crucial information to be giving out. Next slide. All of our information is freely available on our marine portal. So whether you're a large shipping company or whether you are just someone wanting to go out fishing on your rubber duck, you can get the same high resolution information. And we feel this is important because everyday people still need to make crucial decisions about their safety out at sea. Next slide, Mary Jane. As I mentioned, all of this is underpinned by publication. So our published forecast system is available in the published literature. And here's an example of our storm surge calibration. So on the top, you can see how the modeled surge compares with the measured surge. And in the green kind of circles, you can see that Cape Storm peak that we can capture very well. Also to mention is that we also can forecast negative surge. So when the water levels are pushed below the tidal range, and this is important as well for shipping and ports, port authorities to know. Of course, with a numerical model, you can play around with the physics. So we wanted to look at what was driving the surge during this event. So we are able to turn off wind pressure and waves within the model. And what you can see is in the green and yellow dashed lines on this graph, where we turn off wind and pressure, we almost get no storm surge signal without these two factors. So really important to capture these correctly in the atmospherics. But when we turn waves off, you still get the good signal. However, the storm peak itself around that big event, around the 7th of June, is much lower. So it gives you good information on what we need to get right and how important actually waves are to recreating the storm surge signal. So really good high resolution wave information is crucial to be able to also be producing a good water level forecast. You can go to the next slide. Prior to this, also very important to produce a water level forecast, we also need to get the tide right. So one of the first steps to this successful system was calibrating and validating a tidal forecast system. And this is also in the published literature, and also some cool scientific work also in there. Things like looking at semi-diurnal coastal resonance along the south coast as a result of the broad continental shelf that exists there, and some other cool scientific questions we asked in that paper as well. You can go to the next slide, Mary Jane. Next slide, actually. So some of our projects that we're currently have done and are busy doing, and maybe the most important one for the CHPC colleagues is our long-term marine modeling that we're trying to do. So through the help of some of your colleagues, which we're really, really grateful for, we've been able to run our coupled modeling system on the CHPC. And this is with the computational cost, with the extra computational cost, we're able to run longer term simulations. So what we've tried to do is we tried to force our model with ERA 5 data over a 40-year period, so all reanalysis data, in order to give us long-term climatologies of both waves and water levels. So in particular for water levels, this is something that is pretty new to our coastline. We don't really know a lot about storm surge in particular around our coastline. So really good information on us being able to understand how storm surge works. And so you'll see on the right panel, bottom right panel, an initial analysis of 50-year and 100-year return periods for storm surge. So you can see by that, the South Coast seems to be a hotspot. We're still busy trying to finalize this data set on the CHPC. And after that, we'll write up a couple of papers on some of the data. But there's also extra potential for this data set as well. So looking at machine learning techniques to train a climate projection kind of wave and water level projection is something we're also looking at, and some other applications for this data set as well as allowing other research groups to look at some of the data and discover some other things with it. So I think a really cool data set in the end. Next slide, Mary Jane. Another project we're quite excited about is our ensemble forecasting. So because our main model is deterministic, we're looking at some of the addressing some of the potential uncertainties in the forecast with a 8-member multi-model ensemble. So you'll see in the bottom right, the forecast is just a forecast. Sometimes it goes wrong. And so to address those uncertainties, we hope a model ensemble will look at some of both the offshore wave uncertainties, as well as some of the wind wave uncertainties, as well as some of the water level atmospheric driven uncertainties within our modeling system. Next slide. A project being led by my colleague Mark de Vos is looking at high resolution coastal circulation modeling as well. So our current system only looks at water levels and waves, and we're looking at bringing in circulation as well into the picture. It's important because it has quite a few applications, such as search and rescue, water quality. So will it be a blue flag beach day at Clifton today, for example? And the ports also have some applications for it. So a product we are busy developing and quite excited about. He's tested it so far in the Cape Peninsula area, and also looking at some sciencey questions related to circulation, wave-driven circulation as well. Next slide. A project we've run in partnership with the WCSSP project and Plymouth University is a rip, current, and coastal overtopping forecast model. So this takes in water level and wave information from our operational high resolution system and produces the risk for rip currents as well as coastal overtopping at certain locations, also being run and trial around the Cape Peninsula at the moment. But we're hoping soon to operationalize the system and also potentially extend it around the South African coastline. Rip currents are very, very important for search and rescue, as well as sort of disaster management authorities. Quite a few people get caught in rip currents every year. And coastal overtopping, you know, when you see those massive waves in big storms, smashing over coastal infrastructure, that's essentially coastal overtopping. And so to be able to predict that, to give good impactful alerts to different organizations will be quite important for us going forward. Next slide. Another project that we've done is looking at coupling surface currents into our regional domain. And this gives us can give us information on potential wave steepening, especially in the Agulhas current system. And what we see is that by coupling global surface currents into our regional domain, we can actually give a better prediction of wave heights along the East Coast, especially in the path of the Agulhas current. And we also see that when wave directions directly oppose the Agulhas current, you can get massive increases in the significant wave height, up to 60% from what is predicted by global models. So really showing a lot of uncertainty in the global forecasts, and also giving good information to ships that may be going along this route, which is quite a busy route along the East Coast, for potential for rogue waves. Next slide. A project we're also trying to get off the ground is potential sea ice edge modeling in the Southern Ocean. So our area covers Met Area 7, which borders the Antarctic sea ice edge. And so we're trying to get an idea of where ships can expect to encounter sea ice and where they cannot. It's a WMO recommendation, something we're trying to bring into our forecast process as well. Next slide, Mary Jane. Some future potential work. We want to upgrade our SWAS framework further, so with additional science and physics configuration changes, and also extend our forecast lead time to 5 to 7 days. Again, this has quite a large computational cost. So again, a project that we might call on the CHPC to get involved in. And things like tidal changes with respect to sea level rise and climate change related effects on our wave climate and storm surge climate are things we're trying to do going forward. Next slide, Mary Jane. So just to sum everything up, you know, the CHPC is critical infrastructure for the weather service in all our numerical modeling efforts, both in, especially in research and development, but also in operations. Without the research and development done on the CHPC, our operations would suffer as a result. So very, very important collaboration for us as the South African Weather Service. And recently, the Marine Unit has taken up assistance from the CHPC. And this is really enabling research growth in the maritime forecasting space as well, which is relatively new to the Weather Service. So we are extremely grateful for this collaboration, both in the terrestrial forecasting sense and in the marine sense. And we look forward to this collaboration now and in future. Thank you very much.
Thank you very much, Michael and Mary Jane. This is indeed very interesting. I really enjoyed looking at this concise, but obviously very involved way of working that the source is doing, and the different areas that you are touching on. I mean, it is amazing to see. And Michael, especially on the marine research side, I think maybe this is the area that is not so known to people, and I think this was very good to put in this way. We have a number of questions. We might not get to all. I've got questions, but I will leave mine to last for the last ones if there's not time. But we also have Dr. Happy Sithole on the panel now. Happy, I'm going to hand over to you first. I see you posed a question or two there. Dr. Sithole is, of course, the Center Manager for Nikis, and of course also responsible for CHPC. So Happy, I'm going to hand over to you first, and then we can get to some of the other questions.
No, thank you, Werner, for the opportunity, and to Mike and Mary Jane, thank you for a very comprehensive and exciting piece of work that we are doing on HPC. I think when we look at this and what the remit of HPC is for the benefit of the community, you guys just demonstrated how important HPC is for our readiness, our survival, and also in improving our economy. I think what Michael, you are showing about the coastal implication to this, if we look at the ports, such information, I take that it will be very important also for the ships when they go for docking. I recall well in the West Coast, you might recall the ship which ran aground there, Sally, which was waiting to get to the port. And they did not know this information. And whilst they were there, then the ship, as it was waiting to get to the port, it ran aground. Massive losses in shipping. So I think these are some of the things that needs to be highlighted on the impact on the economy. And so thank you very much for this piece of work. And I hope you could be able to package a lightweight type of this presentation that we can also carry it with ourselves. When normally we are asked what does the CHPC or NICIS do, we need to be able to showcase some of this. So not in details, but 2 or 3 slides from all the slides that you put. I know it's a huge task, but maybe you could be able to sample them for us. I think one of the questions that I'm looking at now is that mainly that we are at a stage where we are looking at revamping our HPC systems. I know that SWAS is also in that process. One question is, how big should we go? And what are this looks like there are monstrous challenges that will really consume lots of computational power. And whether you guys, maybe from your other colleagues everywhere, you have seen how much of these resources are needed, so that in our planning and in our strategies, we should be able to give those projections. Thank you very much, colleagues.
I'm not sure, Mary Jane, are you able to answer that? How big should we go? 10 petaflop, 20 petaflop?
I can't give an exact number. We definitely need much bigger systems than what we've got available. So I'll just speak to the operations we have at SWAS. To make those simulate over SADC with 4.4 kilometers that I showed in one of the figures and 1.5 kilometers over South Africa, we use 1,728 cores for that, and the simulation takes it takes over an hour to produce 72-hour simulations. So when you look globally, you find that there are ensemble systems that are being run. So ideally, with the type of simulations that I have just described, you want to have multiple of them. And secondly, there are people that are now moving towards updating these simulations hourly. At the moment, with the resources we have, we update 4 times a day, so which means we update every 6 hours. I mean, with Michael's work also, he showed that they update twice a day. So if you look internationally, there are those that are moving towards updating every hour. So in terms of the systems we need, so you can tell that with what we have, actually, we are still limited. The current models, the UK Met Office, as well as DWD in Germany, they are working towards preparing the models for the exascale. So I see there's a question to say, should we be preparing for that? We should also be thinking about that, because that is what, in terms of model development, that is where things are moving. And I think we had some engagements this week, where there was talk about, whether models not being ready for like GPUs so I think these are things that we need to be thinking about, because we are also getting into the model development space. I hope that answers that.
No, thanks. Yeah, no, that was good. At least it gives us some indication. And also on the part of the accelerators, it should be borne in mind. I think we've got, checked on the list here, our colleagues from the software development, Benjamin Bach is here. I think that's a challenge that they should start looking at to assist taking this and putting them on accelerators. Let's see what could be done. It will be an interesting task. Thank you.
Thank you, Happy. So let's just get to one or two of the questions posed. One is from Audrey Masizana, and this is to you, Mary Jane. He says, we cannot access the mic, so I'm just going to read. He says, a fantastic and exciting presentation. Just a quick question. Is there some formulated decision for choosing a model for a particular country, such as the one you chose for Botswana? For example, geographical factors or so. Do you preference some models for certain countries, or how do you approach this?
It's mostly, I showed one of the slides where we said we compared 11 high impact weather events, and we looked at Cosmo, because we know it's being used in Botswana, in Namibia, as well as in Zimbabwe as an operational model. Here in South Africa, we are just using it as a research model. Then the unified model is the model that South Africa is using operationally. Then there is WRF, which is an American model. So in terms of the decision, there are costs that are associated with these models. Cosmo and UM are associated with a license fee. The UM has got a much bigger license fee compared to the other models. So there is the issue of cost. Like I said, the Americans, they generally make their models available for free. But with the license fee cost also comes support with global output. As I mentioned that in Africa, there is no center that is running a numerical weather prediction model globally. So from the American model, which is free, the global model data you get comes with a grid length of about 25 kilometers, while the one you get from the UK, which as I said, comes with a license fee cost, comes from a global model that runs with a grid length of 10 kilometers. And from Germany, it comes with a grid length of 13 kilometers. So there are a lot of things that and also if you're not paying anything, there's no technical support that you can get from the model developers. But as I mentioned, towards concluding, we are also thinking into building the model development capacity so that, going forward, we don't think about who's going to give us support. We want to be able to give ourselves the support that is needed.
Yeah, I can hear from how you answered, Mary-Jane, that this is a multifaceted approach. And I suppose the more different models you can employ for the same problem, it is only giving you more information to make it more accurate. So thanks for that. We're going to just activate Chiamo. Maybe it's very appropriate, Chiamo. I suppose you're calling in from Botswana. And you are also asking a question on maybe how SADC countries can contribute further. Benjamin, I don't know, is Chiamo able to talk to us? Chiamo, can you talk? Benjamin, maybe you can just confirm?
Sure, we'll do so.
Chiamo, what's your question?
And I also see there's Moai.
Yeah, I see you added Moai, but we're looking for Chiamo, Benjamin.
You can get Moai to go on so long.
Yes, Moai, maybe you can pose your question. Thank you very much. Molokua.
Yes, this is Motula Koa. So basically for me, it's not a question, it's a matter of a comment to say that on the CHP infrastructure, as climate modelers, we produce a lot of data. And then we are requested after 90 days to basically remove that data and process somewhere else. The challenge that we face is that we cannot process this data outside of the CHPC because it requires a lot of resources. So I just don't know what is the CHPC doing about that. I'm sure we all have that same challenge with Mary-Jane as well of processing data.
Yeah, Modula Koa, I think on the chart, I did put in the response there. As I indicated, we are in a process of upgrading our HPC system. And one of the challenges that we have also seen is the storage requirements. And if you guys can assist us in this planning, at least to understand how much of scratch space do you need? And after that, how much of the long-term storage you need that is closer to the scratch? That will really help us. We already know we have got a challenge in our storage policies for people in the climate or the earth sciences modeling. So, yes. But we need some numbers. And this will help us because we are now developing a 10-year plan and we like to solve problems of storage in that 10-year plan.
All right. No,
not sure if Anna, you want to add on that.
Yeah, maybe not to take up too much time, Molokua, but this is definitely being addressed. And maybe we should have a bit of a one-on-one chat, and then I can give you a bit more information. There is very imminent relief that is coming to users soon, but we can take up that discussion. I would just like to hand over to Chiamo. Chiamo, I see you're on the line now. You're most welcome.
Yeah, thank you. Thank you very much. Thank you very much, Verna, and good to see you happy and the background there. A long time ago before COVID, I'm sure we're having this conversation in Cape Town somewhere, but we're in the new dispensation. Just to appreciate the presentations by Dr. Bopape and Dr. Barnes there. Very good work, and it's already showing some very good scientific outputs, really showing that some groundbreaking work can be done in Africa, can be published by Africans, and this is great, especially putting us on the map. But the question is this: so from Dr. Bopape's presentation, the work involved a number of countries in SADC, and I wonder what could be done more at a regional level by countries themselves that are so there in the presentations, in terms of maybe supporting this work and furthering it, maybe in line with what Dr. Sitolo was talking about. What will be required to take that work forward to make sure that it has the impact that is required? Thanks, colleagues.
Okay, I think I'll answer, but I'm assuming the question is also to the CHPC, so I guess Happy and Werner will also add to the answer. So I think from the experience that we had from the project, first in terms of the different countries that we have worked with, I think there is a need for the med services. So this is specifically with, weather, and climate work. There is a need for the med services in the different countries to collaborate with the local universities, because we found that the people we were working with were really multi-headed. Some were forecasters, they are working shifts, they are looking after observations. So in order to increase the amount of work, basically the amount of research as well as research output coming out of the continent, we need to capacitate ourselves more when it comes to research. And if the med services do not have that capacity, then there is a need for them to collaborate with their local universities. Then there is the issue of funding. To get anything going, you do need money. When the project ended, there were a number of people that indicated interest in continuing with postgraduate studies, to do masters, those that don't have, and to do PhD degrees. And there wasn't really a way that I could help, especially those that were not in South Africa. So I think there is also a need for countries to put some money, forward to support research work, as well as to support, for scholarships to support students, so that, we can get more people doing postgraduate studies. And it's difficult to say one country. For example, we can't expect South Africa to pay for studies at a university in another country. Exchanging money, between countries, we also found was very difficult, because, you need to come up with some service level agreements that different governments are not comfortable to sign. I think I'll leave it there and then let CHPC to add to the answer.
Yeah, I can maybe just in very short to respond from a CHPC resource provisioning perspective, Chiama. Of course, any SADC country has access to the CHPC. If you need to do big processing or even small processing, you can use the resources. So no country should be in a position where they don't have access to proper resources to do research. And this is maybe one aspect that I can just highlight again. So whether you're from Botswana or any other SADC country, if you need to do this kind of work, you can do it. But yeah, this discussion, I suppose, has many facets, and Mary Jane, you are touching on them. So Chiama, I hope within the short time we have available, it is answering you at least to some degree.
No, thank you very much, colleagues. Appreciate it. Thank you.
Good, thanks. We are running out of time a bit, but I note the question from you, Nicolette, and it also refers to data and how we provision data. And I think to the earlier question, and I completely agree. There are certain data sets that are used by many different research groups, and at CHPC we are certainly very much focused on getting shared directories set up so that we don't have duplication of data at the CHPC. So this is definitely something that we can do, and with our expanding storage resources, that will become even more or better provision, so that everything doesn't rely on our scratch luster space. But yeah, that is a discussion that we still need to take further. I see, Bernie, you from Mozambique. I think, if I can remember correctly, I read your question now. You say, source performs operational and research simulations using CHPC computing capabilities with WRF and UM models. Where are the simulation results stored, since CHPC does not store data for long periods? So Mary Jane, I don't know whether you can, because this is now specifically to the source performed runs.
Yeah. So Benny, at SWAS, we have got some storage available. So in addition to the HPC system that we've got a number of servers that our researchers are using. And in terms of storage, we actually have some different tiers. So in terms of disk storage, I think we've got up to about 3 petabytes of storage that we've got available. And then there's also data that we store on tapes. So there are some internal investments that we have made at SWAS to be able to save our data.
Yeah, and I think we can add on also on that from Nikki's level, we also looking at long-term data storage systems, which will include tape. And so we understand that people will still need to keep that data for long. At the moment, the policy has been mainly been driven by the fact that we look at our storage as scratch. But with further data-intensive research from DIRISA, we've got an opportunity now to move some of the data, and we've got about 8 petabytes that we have got access to for medium term. And before the end of the year, we will have 40 petabytes that is also available that will include tape. So our storage policies will start to accommodate more for long-term storage. And we also implement policies that allow for seamless access to that while we're looking at hierarchical storage management. So basically, if your file is not touched for a certain period, it will move from the first scratch storage and be moved to the medium term. If it is not touched for a certain period on the medium term, it is going to go to long-term storage where it will be on tape. So when it is at the long term, then you will have to follow some protocols to request that file from there. So it's not that you will be launching your simulation and expect that ultimately it will find your file that you haven't touched in years. So you will have to go link up into that, and then it is moved into your workspace on the HPC system, and then you can launch your simulation. So those are some of the things that are coming that will help you also with long-term storage.
Thanks, Pia. Just to confirm, recognizing that storage is the crucial aspect in resourcing that researchers are looking for. That's been recognized a long time ago already, and we are working hard to address that. So thanks, Happy, for putting that in perspective. Yeah, we're running quite over time, so I'm just going to focus on the one last question posed by Nyameko Lisa. Thank you, Nyameko. He says, thank you, Mary Jane and Michael, for the fantastic presentation. Then he asks, with regards to sovereign capability model development and the ongoing collaboration with Australia, can you maybe indicate how far we are in terms of producing and realizing a coupled climate simulations to rival platforms like DWD's Icon Suite? So it's a very specific question, Mary Jane, with maybe a difficult answer, but I don't know whether you or Michael are ready to answer.
Yeah, well, thanks for that question. Yes, as you say, Vernak, it is a difficult one to answer. I'll just to some projects that we have got ongoing. We've got some funding from the Water Research Commission, with which we are looking into understanding the subgrid models within CCAM. So we are looking at the microphysics schemes, the planetary boundary layer schemes, as well as the cumulus schemes. We are also trying to get to understand the dynamical core of the CCAM itself, and VETS through Professor Francois Engelbrecht are looking into the ocean modeling. So there will be some coupling there. But we also note that the system, as it is, it doesn't have a data simulation system that is similar to what is available in ICON or in the UM. So that is an area that we also need to be building on. So we've got, because we don't really have a big, program that is funded. So we are kind of doing little by little. So I think it will take us long to get to a point where we say now we've got a system that is really working well. But CCAM as it is a model that is running. We've just decided that in terms of building model development capacity, we cannot start from the very beginning. In my PhD, I worked on a model like that, which had a lot of issues. You have to install a whole lot of different things from the beginning. So Brazil, as well as Norway, the way they initiated their model development work, they started with systems that they knew worked, but had some limitations. So that is a decision that we've also made. So I can't tell you, in how long we will have a system that can, compare to the or ICON. I think that's difficult to say. It will depend on resourcing.
Yeah, thanks, Mary Jane. I hope, Nyabeko, that answers you to some degree. Yes, I think we're not going to get to all the questions. I note there are one or two more, but I'm rather going to stop it now because we're already 1:15. Thank you very much, Mary Jane and Michael, for your participation today. You're really doing the CHPC proud also to be able to convey the message of how successful the collaboration is. So we really appreciate it. And I want to end off just highlighting what Benjamin has posted in the chat. All our research webinars, including this one, are uploaded to our Nikki's YouTube site. So you can see it on YouTube. The link is provided there in the chat if you want to click on it now. And you can also pose further questions there. And we will make sure the panel members get this. Or if you want to make direct contact, no problem. We can provide you with further details. So let's end it there. And thank you very much to you, the panelists, the presenters, and of course, all the people that attended the session. We appreciate your participation and interest. And enjoy the rest of your day and also the weekend. Keep well. Thanks.
Thank you.
Thank you.